Hi everyone, welcome to lecture 1 of Isabelle HOL. Today we will be looking at how to use basic aspects of the Isabelle HOL theorem prover. So if you have completed the installation steps before this lecture, then you should have two things installed. You should first of all have Isabelle, and also you should have the archive of formal proofs linked to it. So I'll show you how you can test if those two things have been installed correctly. So I'm going to first open up Isabelle, the JEdit interactive editor. And this is essentially where you edit your Isabelle code and proofs. And I'll pull it over to this monitor here. Okay, good. And if you have installed the archive of formal proofs correctly and linked it to Isabelle, you will see upon loading test.thy, thy is the theory extension for Isabelle files, you'll see that most things are highlighted in pink. And then if you go over to this theories, this tells you what theories are currently being loaded. And so all of these things are being loaded as part of the complex analysis library that is used in, all of these are the theories that are being used as part of the Jordan normal form matrix theory that we're importing into this file. Right? And you'll see that as soon as this is done loading, all of these pink highlights will now go away. And highlighting and colors are how Isabelle tells you what is going on, right? Pink means loading, and anything that's red is bad, right? If I purposely made an error in this document, you will see that there are a bunch of reds everywhere, and Isabelle is not happy with this, right? And it highlights that this test, which is what we currently have open, is what has the error. Everything else before it is fine, right? Okay, fantastic. Hopefully everyone has that set up. And if you do, we are now going to start a new file, and I'll show you how to set up an Isabelle theory from scratch. Okay, so I'm going to go over to File and press New. And this is a new untitled document, so let's give it a name. We're going to give this theory the name, let's call it In-Class Notes. How about? Right. As part of this In-Class Notes, I'm going to import this library that we will be using, that we will eventually get around to using. And we will begin the document and we will end the document. Right, this is just a polynomial library. It gives us access to rational numbers and real numbers that we'd like to work with. Later on, polynomials that we will get to in the 4th lecture. And you'll see here that this file is currently not being highlighted. It has no syntax highlighting. And Isabelle JEdit will not parse the file until you save it. So we have to save the file. I'm going to name this in-class notes.thy. In-class notes.thy. And one important thing is that the file name must be the exact same as the theory name, or else Isabelle will not recognize the file, including capitalization. So once I save it, Isabelle is now able to begin syntax highlighting. Right? Okay, good. So quick introduction to everything that you're seeing on the screen right now. Right? This is the main text editor area. The way that you type comments is as follows, is 2 parentheses and the stars in the middle, right? Comments go here, and so on and so forth. You can, in general, you want to divide your theory files into sections and subsections for better organization. For instance, here in Sidekick, right, the theory is in-class notes. I can define a new section called How About Basics. All right, let's call it Day 1 lecture. All right, sounds good. And once you save the file, Control S or Command S, depending on what you're using, right, you'll see that this section pops up. Right. Okay, sounds good. A couple of notes on what's on things we have around here, right? Theories is the list of all the things that you are currently loading. We've seen this, we saw this before, right? Sidekick is like an index of sorts, right? The output panel is what you'll probably be looking at the most. And then there's the sledgehammer panel that we will get to eventually, right? Outside of that, there's not too many things here that you really need to know when you're first starting off. And that's pretty much all we'll really look at, right? Okay, sounds good. So let's define a new subsection, right? Where let's just say we want to look at some Isabelle basics, right? So first of all, I want to preface this with saying that Isabelle is very close to a functional programming language, and inside of Isabelle, every single object that you work with has a type. Every single object has a type, right? Functions, numbers, right? Everything has a type. For instance, so some common types that Isabelle has, right? You can work with numbers. Numbers have things such as, you can work with natural numbers, integers, rational numbers, right? Real numbers. There's even complex numbers, right? You have data structures, such as lists, right? Is the main thing. Once you have lists, you have everything. You can define everything else, right? You have things such as you have booleans, you have polynomials, you have multivariate polynomials, m-polys, right? And so on and so forth. There are many, many more, right? Okay, so the first little bit of Isabelle code that we are going to write is just evaluating some basic syntactic expressions. So I mentioned that everything has to have a type. And you can one of the easiest things to type is to use the value command, which essentially prints the value of the expression that you're working with, right? So if I type the value of 1, Isabelle is actually going to complain that essentially because it doesn't know what type 1 is, right? I can specify that 1 is an int. I can specify that 1 is a natural number, right? And it'll, in the output, it'll print to me that this quantity is of type int, right? This double colon is the command that you use for specifying what things are, right? What type things are. For instance, I can have a list of natural numbers. Right? I can specify that this 1 in here should be treated as a natural number, and I can type in the rest of the list, and it'll infer that the rest of the numbers are all natural numbers. And Isabelle is able to infer other data types based on if you first fix the type of something, right? In general, you cannot have something. You cannot have different data types within a single list, so you can't write something like 1 nat and 2 int. Oh, actually, it just casts it. Well, you can't do something like that, for instance. So for instance here, if you try to define a list where 1 is a nat and you try to make 2 an int, it will just cast every single thing into this as an int because it's able to, infer, it's able to be pretty smart and say that, okay, well, a nat can be treated as an int, so it just automatically does the conversion, right? But this is not, as a whole, this entire object is an int list, right? Okay, sounds good. The next thing that we can look at, right, is we can look at some list operations. So for instance, maybe I'll start a another subsection for some basic list operations. No, not a sub, just a subsection. And show you some of the things that you can do to lists. One of the things that you can do is, for instance, making a list longer, right? If I have you can have the cons function that takes a element, such as 1, and puts it to the front of a list, such as 2, 3, 4, 5, right? The value of this expression, right, is this simplified expression, right? 1, 2, 3, 4, 5. as a nat list. And because we specified that this one is a nat, right, it's able to infer that the overall list is a nat list, right? If I had, I could do something different, right? I could say something like cons of 1 and say that this second list is actually a real list, and it is going to be able to infer that, okay, actually then this 1 should be treated as a real number. Right? Okay. Another alternate way you can represent this is you can just simply type the pound sign, right? This does the same thing as cons, right? Okay, and this is a very Lisp-like concept. Okay, cool. You can add elements to the front of the list. You can also drop element from a list. For instance, if I write drop 2 of the list 1, 2, 3, 4, 5, it drops the first 2 elements. Right, and you're just left with the last few elements of the list. Alternatively, you can take the first 2 elements of a list, right? Taking the first 2 elements of this list should give me just 1 and 2, right? Drops 1 and 2. Okay, sounds good. You can also access some element of a list. For instance, if I have this list, you can access it with the exclamation point operator. All lists are 0 indexed, so the 0th element of this list is the number 1, which is a nat because this is a nat list, right? The first element is 2, the second element is 3, and so on and so forth, right? If you try to index off of this list, it will let you do it. It just the code generator will just error. For example, if I try to index the 5th element, there's nothing. It'll say exception match raised. It is not able to evaluate this, right? Okay, cool. But 4 will, which is the last element, right? Okay, sounds good. There are a lot of other more built-in functions for lists, right? For instance, you can find the length of a list. You can find the length of this list that we were just working with. The output will just get 5 here. Right, and in general, if you want to figure out, it's not super helpful for me to stand here and list out every single list function that exists. Right, what you can do is you can control click onto a function to bring you to the theory that it comes from. So if I control click on length or command click, it will take me to the list.phi file, the list theory file. And this is the file that defines all of lists inside of Isabelle HOL and all of the other things that you have access to as a result of using Isabelle HOL, right? So, for instance, you can rotate a list, you can zip 2 lists together, right? You can apply filter on a list, you can reverse a list, right? All of these things are in here. If you need something, right, you can always go through and see what is available to you. Now, these 2 buttons up here, the buttons to go back and forth, right? It just brings you to the last location your cursor was, and it's very useful for navigating, for navigating to different places, right? Okay, sounds good. Now, beyond these, right, I'm actually going to go back to the basics section here, to the basics section here when we were working with numbers. You can do some simple operations with numbers, right? For instance, I can take the natural number 1 and add it to 2, and it will plus 2. If I give it proper parentheses, it will tell me that this is the natural number 3, right? I can do things like division. I can do 6 divided by the rational number 2. It'll tell me that this is 3, right? If I try to change this to an int, it's going to tell me that you can't do division on integers. Isabelle does not define that. So this has to be a rat, right? And in general, even though value comments can, just show you, do these like simple calculations, that's not the point of Isabelle, right? Like if I try to do something like the square root of 4, right? Square root is a well-defined function. It's a function that takes a real number and outputs a real number, right? it's not, the valid command is not able to calculate it because Isabelle does not have code for computing the arbitrary square roots of real numbers, right? And it's not built for trying to do that, right? Isabelle is at its heart an interactive theorem prover meant to state and prove mathematical statements. So valid commands are nice for testing code, right? Running basic things, but really you want to prove things, right? So let's get into the heart of what Isabelle is about. So let's state some simple lemmas, right? Let's stating some simple lemmas. How about that? Right. So, for instance, for the square root of 4, we might want to say that it's that the square root of 4 is equal to 2. So you can write something like a lemma. Whenever you write a lemma, you should give it a name. I'm going to call this lemma the square root of 4, where where I state that the square root of 4 is in fact equal to 2, right? Okay, cool. And when you are trying to first solve something, right? This is a goal. This is a sub goal. The first thing that you should try is try 0. Should be the first command you try to attack a statement, right? Essentially what try 0 does is that it will try all of these different search algorithms. They're very simple, they're very cheap and fast search algorithms that will try to directly solve this goal. And you can see here that we get 4 distinct proofs, right? You can use either one. In this case, I'm going to, let's say, use by simp, right? You can either click it, and then you can go back and delete the try 0, right? Or you can just, right? You can just remember that it's by simp and just type it, right? Okay, sounds good. Okay. Now, it's not always the case, right? So, you know, sometimes you might encounter lemmas that are slightly harder, you know, statements that are slightly harder to prove that try 0 will not be able to prove. So for example, take a look at this lemma. I'm going to paste it in and come back. Okay, so this is a lemma that says that if a natural number x is greater than 1, then its square should be larger than itself, right? Slightly more complex theorem. Here, if we type try 0, well, actually, we don't really find it, right? It's not able to find a proof with any of these algorithms. What I'm going to do for now is just sorry this out. All right, you can see before I typed sorry that we have a little bit of red, right? Red means, remember, red means bad. And the way that Isabelle wants you to approach things is that if you can't prove something immediately, please sorry it out, right? So that as a reminder that you need to go back and prove that. So, okay, good. We saw that try 0 didn't work, right? So the next thing up is you should just try sledgehammer, right? And sledgehammer is one of the main selling points of Isabelle. Sledgehammer is many decades of research of search algorithms consolidated and automatic theorem provers consolidated into one tool that essentially does a very deep search of all of the available facts that are you have access to, and it'll try to pull them all together, right? So you can see in this sledgehammer call that we used all of these. That Metis is the search algorithm we used. Assumptions was this fact right here, that x is greater than 1, right? In general, whenever you want to refer to the assumptions of a lemma, it's abbreviated as ASSMS, right? And then it found a whole bunch of these, you know, lemmas that were useful to it, to helping it prove this fact, right? You can try to click into one of them, right? This is a fact. Well, okay, that's harder to read, but right, this is a fact that says that a to the power of 1 is equal to a, right? So it's able to, you know, combine together, you know, all of the lemmas that it thinks it needs to prove this statement. All right, so sledgehammer, very good. If try 0 doesn't work, right, sledgehammer a lot of times can solve it. Okay. Now, in general, you shouldn't just sledgehammer every single, every single subgoal that you run into, because, then at the beginning, a lot of times you're going to encounter the phenomenon of you're just staring at sledgehammer run away, and it's going to time out and not quite be able to solve things. So really, the way that you want to approach proving things within Isabelle is by breaking things down. We're going to see an example of this. So let's say we want to prove this numeric inequality. I'm going to paste this in. We want to prove a numeric inequality that the square root of 2 plus the square root of 18 is less than the square root of 80, right? For now, maybe we're not able to solve it. And in fact, if you run sledgehammer on this lemma, it won't be able to find a proof, or at least I don't think it will with my current iteration of sledgehammer. And so what we need to do is we need to break this proof down into simpler steps so that automation can close the gap, right? What I'm going to do right now is start a proof block for this, where this block of proof, starting from proof dash to QED, is exclusively dedicated to showing this statement, right? So in the middle, we have show thesis. This is the thesis. And we're going to say sorry because, we haven't been able to prove the thesis yet, right? So let's try to sketch out this proof, and then we're going to, just maybe in like a comment here, right? And then we're going to try to turn our proof sketch into proof code, right? Okay. So first of all, it suffices to show that if I take the left-hand side squared, right, that if I can show that this thing squared is less than the right-hand side squared, which is 40, right, then yeah, then we're done, right? So we can think a little bit about what the left-hand side squared here is. So this thing squared is equal to so a plus b squared is a squared, which is 2 plus 2 times a times b plus b squared. Square root of 18 squared is just 18, right? And then you can go through, right? But then, well, this is actually equal to this is 2 plus 18 is 20 plus 2 times the square root of 2 times the square root of 18 is the square root of 36, right? And then all of this is equal to 20 plus 2 times 6. And that's simply equal to 32, right? And this is indeed less than 40. So, right, so this is going to be the way that we're going to try to prove this statement, right? So let's start off from the top, right? And begin going through line by line. So first of all, we were saying that it suffices to show this, right? We were trying to say that if we can show that the left-hand side squared is less than the right-hand side squared, then that's enough to close the gap to the thesis. We're sort of working backwards a little bit here, right? So I'm going to copy-paste this statement. And the way that you introduce a subgoal in Isabelle HOL is with the have statement, right? So I want to say have that this thing is true. Remember, all statements in Isabelle go inside of quotes, right? I'm going to sorry it out for now. The proof of this is, is going to be somewhere here, right? That this whole thing is equal to 32, right? So if I were able to prove this, then I could show the thesis. Then I could try to show what we were originally trying to show, right? So just to show that again. Before I typed it then, the thesis is the same as what we were showing, right? After I typed it then, it takes in this fact that was right before it. So then is sequential. It just looks at the fact right above it, and it pulls it into the proof context, right? It's able to use the subgoals, right? That says, okay, suppose we were able to show this, then we can show this final thing, right? See if try zero does it. Try zero does not do it. Let's see if sledgehammer does it. Sledgehammer hopefully does. Good. Right, and then we can delete the sorry. And if you're really curious, right, real less square root, all it says is that if x squared is less than y, x is less than square root of y, right? That's exactly the statement that we were using to go from this step to this step, right? Okay. And then in order to show that this thing is less than 40, well, we made a calculation, right? We made a calculation that this thing is equal to 32. And of course, 32 is less than 40. So really another intermediate subgoal that we can try to prove is that this thing is just equal to 32, right? If we have this statement, then of course this statement will hold, right? So I'll say then have, right? To say that I can use this subgoal to close out, to prove this subgoal, right? That's equal to 32. 32 is less than 40, right? Simp is able to solve it. Good. Right? Now we've reduced our arguments down to just these two lines, right? Okay, sounds good. So let's try to focus on just this, right? At this point, I'll show something a little bit fancy. This is a very nice, like small and simple fact that we can try to prove, right? That we can try to focus on. This is the only thing that we need to look at for now. So we can start another proof block. I can replace this sorry with a proof block for prove, show thesis, sorry QED. And in general, you can nest as many proof blocks as you want, right? But once I do this, I now have a new proof block where I only have to worry about this goal, right? So this, just for helping me, so that I can do whatever I want in here, and it only affects the proof of this statement, right? Okay, so let's see how we are going to prove this, right? I first want to show that this thing squared is equal to this, which I can just copy paste, right? We want to hopefully show that this is true. Let's see if this will work. Does not. We are going to try sledgehammer then. Good. Okay. All right. Sledgehammer is able to find the proof pretty easily. Then the next step is to show that whatever this was is equal to that, right? So turns out that you can. I was using this ... as sort of like, like that really should be like pasted here, right? Okay, so I'm going to explicitly write that out, that this right here, that the new right-hand side should be calculated as such. Let's see if it's able to find it. Nope. We're gonna try sledgehammer. Okay, sledgehammer finds a proof. Very good. Right, and in general, as long as if you find something that you think should be true but isn't immediately obvious, right? Break it down into more steps, and sledgehammer will usually be able to close out. Will usually be able to close out the proof as long as you break it down enough, right? Okay, cool. And then we wanted to say that this whole thing simplified, that square root of 36 simplified to 6, right? So I can do that. That this is equal to this, right? See if try 0 does it. Simp is able to solve it. Very good. And then, then I want to show that this whole thing is equal to 32. Right? Simp. Oh. Okay. And this is a good chance to explain something about type inference. So before, if you see all of the statements here had something about square root. Square root is a function that explicitly turns things, casts things into real numbers. And so in this expression we were working with just now, we no longer have a square root, and Isabelle actually doesn't know what type this 20 is, right? It thinks it could be an int, could be a nat, could be something, modulo 73, right? So we have to tell it that actually we're still working with real numbers, and it will be able to infer that the rest of this equation works with real numbers. And so this is, and now try 0 will work simply by simp. Right. A lot of times you're going to run into issues where they're like, "Oh, this is just simple arithmetic. Why isn't Isabelle able to do it?" It's because you're missing some explicit typing information. Right. Okay. Good. So now that we have all four of these, right, the first statement, all four of these statements, these were 4 steps and transforms them one by one. And we should be able to show the thesis, right? But we want to use these 4 statements. And the way that we can use them is by labeling them, right? If you label a statement, you can you can refer to it later, right? So I'll label this as step 1. This is step 2. This is step 3. This is step 4, right? And then show thesis, if I say using step 1, step 2, step 3, step 4, right? This series of steps, it will prove it by simp, right? Okay, fantastic. Another thing that I wanted to show off, right, is that this is one way to do it, where you can manually, try to visually track that, yes, the right-hand side of this first bullet is the same as the left-hand side of the second bullet, and so on and forth. And, we were pasting it, so we know that's true. But it's, something that's somewhat nice to lessen the visual load on your eyes when you're trying to do Isabelle proofs is we can start with S1, right? S1 tells us that this left side unfolds into this. And then instead of using S2, we can do, oh, actually, hold on. We don't even have to use S1. We can, instead of using S1, we can actually do unfolding S1. And all that will do is that it will replace the original, right? Originally, it was square root of 2 plus square root of 18 squared. It will use S1's rewriting rule to replace the left-hand side with the right-hand side. So in general, unfolding always replaces left-hand side with right-hand side in line, right? We didn't have to clutter it up, right? So we unfolded S1. Then S2, right? This matches exactly with the left-hand side of S2. So I can do unfolding S2 next, and it'll, do that. It'll rewrite it into the right-hand side of S2. The right-hand side of S2 matches the left-hand side of S3, so I can do unfolding S3. Right, that's very nice, and unfolding S4, and actually gets us into dead simple. Of course, 32 equals 32, right? What is it? By simp, by blast, right? Anything will work at this point, right? Okay. Just another way of doing it and showing off this new unfolding keyword, right? There is a proper way to do this using calculational reasoning. I will have an example of that in the actual notes that I send out that you can see, but I wanted to use this as a chance to demonstrate the unfolding keyword. Right? Okay, sounds good. Let's look at another example. So here, I've pasted this example about rational algebra, about the algebra of rational expressions, that says that if we fix a variable x as a real number, and we assume that x is not equal to 1 or negative 1, then 1 over 1 minus x plus 1 over 1 plus x should simplify to 2 over 1 minus x squared. Right? And so, as always, we're going to sketch out a proof, and then we're going to try to, turn lines of the proof into Isabelle code, right? I'm going to start a proof block here. Proof, show thesis, the usual shenanigans. Sorry, QED, right? And then I'm going to try to just sketch out the proof in a comment here, and then we'll, slowly turn the comments into an actual proof, right? So, okay, of course, we're going to want to do common denominators, right? The first thing we'll try to rewrite is that, okay, this thing is equal to itself times the quantity 1 plus x over 1 plus x, right? Which then is equal to 1 plus x divided by the quantity 1 minus x times 1 plus x, which is simply 1 plus x over 1 minus x squared. Right? I want to be clear about where my parentheses are. Good, right? So this first thing we can rewrite into 1 plus x over 1 minus x squared. The second thing is very similar. If you just multiply, the second thing is 1 over 1 plus x. Then you just multiply by 1 minus x over 1 minus x. And this will just be that, right? 1 minus x over 1 minus x squared. And so in total, right, the sum is going to be equal to this thing plus this thing. The minus x plus x cancels, which is 2 over 1 minus x squared, right? That's the proof sketch. So we have one sub-goal, we have a second sub-goal, right? And we should be able to combine them together. So let's try to write that, right? So let's say have goal 1 is the fact that this thing, we want to eventually show that this thing is equal to this thing in the end, right? I'll sorry it out for now. We'll come back later to prove it. And then goal 2 is that 1 over 1 plus x is equal to 1 minus x over that whole thing, right? Then we want to show thesis, right? So goal 1 lets us rewrite this expression as that expression. So I can go ahead and do unfolding goal 1, right? It'll just replace the that expression in line. Unfolding goal 2 replaces that in line. And then, you know, hopefully the simplifier can see, right? So let's see, try 0. Yeah, algebra is able to solve this after we have goal 1 and goal 2 completed, right? Okay, cool. So now I'm going to go individually into goal 1 and into goal 2, right? And here I highly recommend, I highly recommend that you pause and try to, solve these goals by yourself, right? At any point before I show a solution, I recommend that you pause and try to attempt it yourself first, right? This goes for the rest of the lectures. So I'm going to go ahead and turn this sorry into a proof block. Show thesis, sorry, QED. All right, we're trying to show that this is true. We know that this is the first line that we wanted to start with, so I'll go ahead and have that, right? And this is only true if you can, you can always take a fraction, take any number and multiply it by 1, provided that the numerator is, provided that this is actually equal to 1 and not 0 over 0, right? So we need the fact that x is not equal to -1. Right? As long as x is not equal to -1, this fact holds. So we need this assumption. And the way we use that is we can say using ASSMS for using assumptions, and it pulls in all of the assumptions, right? At this point, you could prove it, but if you wanted to, right, be a bit more precise, right? This is the only one we wanted. You can pick out just that second bullet by typing in parentheses 2, right? And it'll just pick out this second assumption for you. Okay, and this should be enough to prove that this is true, right? This will prove by simp. Okay, wonderful. And then we wanted to show that actually this left-hand side is equal to, well, yeah, that you just want to multiply them through, right? So we'll have this, let's say try 0 by auto, very nice. And then finally, we want to using, let's call this S1, let's call this S2, right? We'll go ahead and do unfolding S1. Sorry. Okay, this is my bad. Unfolding S1 is not a good idea because 1 over 1 minus x will recursively unfold itself. So don't worry about it. We'll just go ahead and using S1. And S2 and see if it's able to prove it. Not quite, so let's see if Sledgehammer can do some damage. Good. All right, it's able to prove that very easily, right? Okay. Goal 2 is going to be almost exactly the same. I'm going to go ahead and just fill that in, and I'll come back. Right here, because they're so similar, I'm just copy pasting the proof of goal 1 and just lightly modifying some of the proof steps. right? In general, copy pasting is always faster than typing things out manually. Okay, good. That proves it, right? And there we go, right? Here we have decent proof. We've gotten all the sorries, so we've proved the statement, right? Okay, good. Let's look at another example, this time with complex numbers. So here we see a statement about complex 1 to the 8th power is complex 16 to 0. The way to read this is that in general, complex of AB, complex number takes two real arguments, a real part and an imaginary part, is just A plus B times I, right? If you're ever sort of confused, you can always click into a definition, right? It's a complex number. Complex has a real part, has an imaginary part. Okay. Okay. It's okay if you don't really understand what this code is doing. It gives you a rough sense of how this data structure of this data type is built, right? Okay. As always, let's start a proof block. Thesis, sorry, QED, and we're going to sketch out the proof, and then we're going to try to turn the proof into code, right? So first of all, we'll notice that this is complex 1 is 1 plus I, right, to the power of 8. So we could just calculate all of the powers of 2. So for example, complex 1 to the second power is, well, we know how complex numbers multiply. It is 1 plus 2I minus 1, which is just equal to 2I, right? And then we'll be able to calculate that complex of 1 to the 4th power, well, is actually complex of, this thing, complex, 1 plus I squared, and then squared again, which is just 2I squared, which is equal to -4, right? And then if, again, we want to compute this thing to the 8th power, then it's just the 4th power squared, which was -4 squared, which is 16, right? Okay, gives a pretty good proof sketch, and that's exactly what we're going to do, right? Again, try to pause, try to work this out on your own, and I will, right? And then when you're ready, let's come back and look at this. So first things first, right? I want a subgoal that tells me how to compute the second power, right? That this is equal to 2I. The first thing that I'm going to do, well, so the way that we represented 2I is complex of 0, 2. Sorry. Right? And then we want to use this fact to try to prove that this guy is equal to -4, which is complex of -4, 0. Complex, right? You'll see that if I misspell it, immediately it highlights it to visually tell me that something is different, right? Complex -4, right? That's the next thing we have to prove, right? And then the last thing we'll be able to prove is that is the thesis, right? Okay, so let's work on it top down, right? First of all, we were saying that this is equal to that. So I'm actually going to do something slightly different. I'm going to first say that, well, okay, let's go ahead and just do that, right? We know that it should be equal to 2I, so I'll just go ahead and, actually, we don't even need this. I'll just go ahead and sledgehammer this, all right? See if it can find anything useful. It is indeed able to find a proof. I was doing this because I had already ran through this example, right? But cool. And if you sort of look at what rules it used, right? First of all, it uses power 2 equals square. It just says that a squared is equal to a times a, right? Okay, nothing crazy. And then there's this complex mult that actually defines how multiplication of complex numbers work, right? This is useful. This tells you that when you multiply a plus bi times c plus di, it's this usual definition of complex multiplication that you expect, right? Bi times di is negative bd, right? Okay, good. So now on the next one, when we're working on this, right? Well, we can keep this in the back of our mind, right? We know that this is something that's defined, that sledgehammer needs to use, right? So in order to first calculate complex of 1, 1 to the 4th power, we have to know that it's equal to this thing squared, right? So we'll have, let's say, pow 2 squared, right? That this is true. Auto, right? That, of course, this thing to the 4th power is the same thing as you square it and then square it again, right? So now when we're trying to prove this, what we can do is, well, we can unfold the previous line, and we say unfolding pow 2 squared, and it just turns it into a complex of 1, 1 squared, and then the whole thing squared again, right? But, well, we know what complex of 1, 1 squared is. We know what 1 plus I is. I'm going to go ahead and call this fact pow 2. I'm going to go ahead and unfold pow 2, and it replaces it with 2i. So now we're trying to prove that 2i squared is complex of negative 4, 0. Right? We can furthermore use this fact, right? This was the thing that, Sledgehammer kept on trying to use. It was the thing that was able to, take squares and say, okay, something squared is itself times itself, right? So I can furthermore take this fact and keep on unfolding it, and you can see that it just turns into, oh, actually I didn't quite want to do that. I'm going to go ahead and go to the next line and unfold it. Right. Sometimes when you unfold a bunch of things on the same line, the order of which things are unfolded can be a little bit opaque. So I know that I want to unfold the first 2 facts first, and then I only want to unfold the squares, the a squared equals a times a fact on this result. Right. Okay. So we get to this step here, right? And then we know that we are going to be using the complex mult definition, right? This is the complex mult definition that we were using. We know we're going to have, or we have to be using this. So the way that you can read this now, right? This looks a little bit different from what it looked like when we control clicked into it, right? When we control clicked into it, this was just A, B, C, D, right? But now we have this question mark A, right? This question mark's in front of it. And what that means is that we can instantiate those variables with any values that we want, right? We know that we want to be performing this with, we know we wanted this to be replaced with 0, that replaced with 2, that with 0, that with 2, because that's what we were trying to prove, right? Is that 2i times 2i result, right? And the way that you can instantiate a fact in Isabelle is by using square brackets, and you type of to go to instantiate variables from left to right, right? Anything with a question mark can be instantiated. So that A, we want it to be a 0, right? If I type 0, it immediately replaces that in. That B gets replaced with 2, right? And again, C is 0, D is 2, and now it's able to tell us how to compute this, right? 0 minus 4 is negative 4, 0 plus 0 is 0. And now, even try 0, we'll be able to solve this goal, right? Okay, very good. Alternatively, if you had just sledgehammered this, it would have found it, right? Sledgehammer absolutely would have found the proof for this. However, it is good for us to know, go into a little bit of detail of how exactly we can manipulate the proof state using different commands, right? It's able to find all these proofs. This whole, it's able to just combine it all into one, right? Rather than a more manual way of what we did by massaging the proof state, right? Okay, that's okay. Good. I'm actually going to just let Sledgehammer finish off this last sub-goal right here, right? You could, do something similar and try to break it down more, right? And yeah, right, and do it more manually. But Sledgehammer here is good enough to do it. Right? So we'll let it close that off. Right, and it was only able to do, I remember, because we proved this fact, right? That we broke it down a little bit. I believe if you had maybe tried Sledgehammer at the very beginning, it's not going to be able to prove it, right? Just a note on the output here. This means that it's explicitly referencing this fact that we proved, which is this, right? It's explicitly referencing this because we didn't label it. If I called it POW4, if I call this POW4, we can actually replace this with the name that we gave it as POW4, and the proof will still go through, right? Okay, fantastic. Let's look at one more example before we leave off this lecture. And in this example, we will see how to split a proof into individual cases and try to tackle each case if it's easier. So this reads that for any x and y as real numbers, if their product is 1, then their sum cannot be 0, right? So I'm going to start a proof block here, proof, show thesis, REQED, right? And we're going to try to sketch out the proof. Essentially, the proof is going to split into 3 cases, right? Case 1 is going to be what happens if x is positive. If x is positive, then y is positive, right? Because their product is a positive number. So if one is positive, the other must be positive. And thus, x plus y is positive. And so it's not equal to 0, right? Case 2 is similar. X is less than 0. If x is less than 0, then y is less than 0, and thus x plus y is negative, right? The final case, if x is not positive, x is not negative, then case 3, x is equal to 0. But then we have that x times y is equal to 0, which contradicts the assumption xy, right? We have an assumption labeled xy, right? Contradicts the xy assumption. So this case 3 is impossible, so we shouldn't need to consider it, right? We'll see we'll see in a little bit of how we should technically formalize that, right? Okay, cool. So the way that we break it into these 3 cases, right? These are 3 exhaustive cases. All proof by cases in Isabelle must be exhaustive. Is we use these curly braces blocks. So in block 1, I'm going to assume, right? Let's call this case 1 that x is greater than 0, right? Maybe let's even name it something a little bit better. Let's call it x pos, right? X is positive. If we assume this, then we need to show the final conclusion, right? In this case, we need to be able to show that the final conclusion holds. So we'll write have the conclusion, right? Rather than writing this, you could also type have thesis, right? Because remember, the thesis is exactly the same as that line right there, right? So this is case 1. Moreover, we want to prove in the second case that when x is negative, you can also prove the thesis. And lastly, right, what happens if x is 0 equal to 0, you also want to prove this thesis, right? We are going to go back and prove each case, but first we're going to make sure that these 3 cases are exhaustive. And so this last part right here is an exhaustive. We need to show that these 3 cases cover all our bases. So we'll write ultimately shows. And you'll see after I write ultimately, it pulls all 3 of these cases in, right? If positive, then we have our conclusion. If negative, then we have our conclusion. If 0, we have our conclusion. So we always have our conclusion, right? By linear arithmetic, we can get rid of the sorry, right? And now we can go back to each of these cases and work on them, right? Once again, I encourage you to pause, try to work through these cases yourself, right, okay. So let's try. We'll follow our proof sketch, right? We want to show that y is greater than 0, so from x being positive, we should have that y is positive. I'll say then have y is positive because x times y equals 1, right? Using xy, right? Alternatively, you could also write using assumptions. They hold the same thing. Try 0 doesn't work. It's probably some sledgehammer proof. Good. Okay, first one that proves is good enough for me. Right, and then half thesis, because x is pos and y is pos, right? So their sum is not negative, is positive, right? Automation is good enough to discover that. Right, this next case should be extremely similar. Instead of y pos, it's going to be y neg. Y is less than 0, using assumptions instead of... Oh, I'm just gonna sledgehammer it again. Right, try to fix the broken proof. Once again, this proves pretty easily. All right, that's the first two cases taken care of. And then using x neg, y neg by simp. Good. Then we have this case of what happens when x is 0. Well, we said that when x is 0, right, we should have the x times y is equal to 0. So, okay, I have this, right, try 0. Sorry, I should say using x0 y auto, right? But then, well, our original assumption was that x times y is equal to 1, but we were able to show in this case that's equal to 0. That's a contradiction. When you have a contradiction within a case, you can show false. So I'm going to explicitly show this, right? You can show the statement false using, this is xy is equal to 0. So using xy 0, that's just what I labeled it. And also the assumption, which is xy, right? That's clearly false. That's clearly a contradiction, so you can prove false. And once you can prove false, you can prove anything you want in the world, right? Using false, false implies anything by blast, right? That covers it. So more formally, the way that we say that this contradicts assumption xy, it's impossible, is that you can prove false, right? Proving false is contradiction. Okay. This is a good place to stop, but I want to point out this case right here, right? We were able to show false in one case of a statement, and this was not an issue because we were just saying that this statement is impossible, right? But suppose that you wrote, right? Suppose that you had a bigger proof file that you were working with. You know, maybe you have some intermediate lemmas that you're not quite sure if it's true, but you're just stating in hopes of, you know, it being true. You know, I can try to write a lemma, right? If you write a lemma or a set of lemmas that together introduces an inconsistency, you will be able to prove false. And if you can prove false, if Sledgehammer can find a proof for false, then from anywhere on after, Sledgehammer will be able to prove any statement. It will be able to first prove false and then use false to prove anything else, right? So a good sanity check at all points in your of when you're working on something is to just run Sledgehammer on the statement false. And if it can prove it, something is wrong, right? You've stated something wrong. You know, you have a sorry from earlier, right? Look for sorries from earlier that you haven't proven, right? By default, Isabelle HOL is sound, so you should assume that all errors are introduced by you. And if you really found a soundness issue, of which there's about one, you know, people usually on average find one like every decade or so, I'm told, then you can report it to the Isabelle maintainers, and we'll have a much more interesting discussion about how you managed to do that, right? So don't do this. This is bad, right? Okay, cool. That's a good place to stop.